Hi, and welcome to our fourth video in our 10-year anniversary series. This video is called The Evolution of Network Protocol Architecture, and I'm Ed Koehler. I'll be your host for this session. Networking technology is not static, and I'm speaking actually in the areas of protocols and protocol architectures. Yet, interestingly enough, many networks today operate on networking protocols that were ratified in the late 1980s and early 1990s. They are layered and they have top-down dependencies, and we're very familiar with these models. We'll look at them. And what I find interesting is that organizations will go out and purchase switching gear to quote-unquote modernize the network, and yet they place these same protocols, again, which are fairly old now, back into the network infrastructure. And yet networking protocol architectures have evolved over time with different interpretations of what networking fabric architectures are all about. And that's what this session is going to focus on. If one will take note of the overall evolution of these models, there is a gradual streamlining and atomization of the network protocol stack over time that leads to greater degrees of scalability and automation of services. One will also take note of the increased importance of virtualization of services across the network and its increasingly tightening bonds to security, policy, and posture. Such attributes, we feel, will be increasingly desirable in the increasingly digitized world. So let's take a look at this from a different perspective. In the past, we've had different protocols, different networking architectures to do different roles within the network. The goal of the evolution is to provide a unified end-to-end fabric using a single protocol architecture that can work in all of these environments. And that's really what we're going to talk about as far as the goal of the evolutionary trail, if you will. This is a look at the quote-unquote traditional protocol stack that we all know and love. I standardized some of these, or at least participated in some of the standards of these protocols. It's a layered construct model. And each layer is fairly independent of the other, and they are largely unaware of the others. And this is in protocol behaviors as well as the control planes themselves. It's a top-down vertical dependency, which can lead to what's termed as a house of cards. If we have failures in the lower-level protocols, such as spanning tree or internet gateway protocols, such as OSPF route flapping, things of that nature, it can actually cause the northbound protocols to fail, and this basically causes a collapse of the network infrastructure. Complex mutual dependencies also require rather strict provisioning practice. There's really ways you should string out a service chain in this environment, and it can be complex, particularly the more protocols that are involved in the overall configuration. It is difficult to automate as a result, and it is also as a result difficult to troubleshoot. But let's take a look at these layers in a different perspective from a functional architecture model. And as we can see, things are a little bit more complex here. We have, first of all, we notice that we have two control planes. One for the IP, which is the OSPF or ISIS, some sort of internet gateway protocol, but we also have an MPLS control plane, and this is either LDP or RSVP based. So we have two control planes that we're dealing with, and then we also have a service signaling protocol level, which is MPBGP, LDP, and PIM for multicast. So MPLS uses many separate signaling stacks and protocols, usually a different one for each type of service, i.e. L2, L3 multicast, and therein lies the complexity of the technology, really. The MPLS data plane, however, as we can see, is fairly simple. It's really just a MPLS label directly over Ethernet, but we also see that we have two data planes here. We have the MPLS data plane, which provides for the labeling, and then the Ethernet data plane, which provides for the end-to-end forwarding. But note that this is a precedent, and I want to return to this later on, this notion of providing labeling and transport directly over Ethernet. And this is something that was one of the key evolutionary goals that we wanted to keep with and achieve, but without the complex provisioning and troubleshooting that we have within the conventional MPLS protocol architecture. There was an evolution over time to slim down and reduce the number of protocol layers, and also a function to condense the service signaling and the control planes. But as we can see, that only succeeded to a limited scope, and this is particularly around IP fabric architectures. And this is the notion that you have an IP routed environment and you can overlay a fabric architecture which is based largely on VXLAN. Now we can see two models here. One is the Cisco campus fabric, and we can see that it uses Lisp as the actual service signaling. We can also see that it uses the same protocol for the control plane as well. And then obviously we have the underlying IP control plane. So we still have two control planes, and the secondary control plane for all intents and purposes is a proprietary protocol. It's Cisco's the only vendor that really uses it, and to my knowledge, this is the only use of Lisp within their architecture. On the right-hand side of the slide, we see EVPN over VXLAN. This is the industry standard, if you will, although I want to emphasize there is no industry standard IP fabric. But most of them gravitate towards some sort of EVPN over VXLAN, and this is something that Extreme supports as well. Notice that the architecture is basically a mirror. The only difference is that rather than using Lisp, we're using MPBGP. But notice how we do have a reduction of protocol layers. However, the layer dependence remains. Virtualization is provided by a variety of protocol methods depending on the vendor, which is why IP fabrics typically do not interoperate with one another. So even if they're following the industry standard interpretation, you can't really take vendor A and plug vendor B together and expect it to work. There are differences in the way the signaling works. IP provides the underlay as well here. We still have IP. And in some instances, some would say, well, that's good because I don't have to rip out my network. I can just overlay this fabric over the IP infrastructure, and that is one of the benefits. But note how IP still is provided and required, and to some degree adds to overhead and also adds to the complexity of a secondary control plane that needs to be managed. Now, as we move on, there was a concept that was developed called shortest path bridging, and that is what Extreme Networks Fabric Connect is based on. It's an IEEE standard of 802.1AQ, wrapped into the 802.1Q standard in 2014. There is an IETF document which largely focuses on the support of ISIS as the signaling and control plane for shortest path bridging, and that's RFC 6329. It's based on the philosophy of ISIS forming adjacencies to neighboring nodes, discovering the core topology, and then automatically calculating shortest paths from itself to every other node within the network. So it's basically a programmed directional graph theory environment. Shortest path links are based on metrics with no block paths. All ISIS adjacencies are point-to-point, and of course we have reverse path forwarding checking, which makes transient loops impossible. There is a IEEE standard for OAM, complies with CFM, and also, which is not necessarily an IEEE standard, but associated is Y1731 standards. Unicast paths are calculated from every node to every other node, and the ability also creates on-demand service-specific multicast delivery trees, which was primarily where I was involved in the development, and it is a very robust capability. We have some customers that are supporting tens of thousands of active concurrent multicast groups within a single core environment. There is no IP configuration required, and there is no IP that exists inside the fabric. This is exclusively an Ethernet fabric technology. We'll give you details on that later on. The network consequently becomes a virtual switched Ethernet fabric. The backbone VLANs provide the different data planes for load balancing, as well as equal cost shortest path trees. And notice again that the network topology and the network path behaviors are provided directly by Ethernet. Now, the best way to look at the architectural model is to compare it with other fabric technologies. And we're going to first compare with MPLS. Notice that our notion of labeling directly over Ethernet is maintained, and this is the architectural goal that we had. Now the labeling is a combination of MAC and MAC, which is basically MAC addresses in Ethernet, and MAC provides us that tunneling capability. And then also the use of ISIDs, which are individual service identifiers, which identify specific tunneling and forwarding environments within the Ethernet core. So by that, what we can do is we can condense everything down and remove the need for a secondary control plane. We also remove IP. It's only ISIS directly controlling the Ethernet behavior, which is SPBM. Very, very clear. MAC and MAC tunneling is basically the ISIDs themselves, and we can support 16,777,215, which coincidentally is the same as the VXLAN environment. Then there is a service signaling above, which is again collapsed, and ISIS and Fabric Attach. Fabric Attach is another IEEE standard, which currently is in draft in the latter phases, so it's ready to become a standard, which is called 802.1qcj, and that handles the attachment of Fabric Attach or Auto Attach intelligent switches and also wireless APs. We have vendors with video surveillance cameras that also support this protocol as well. So now, as you can see, everything is streamlined down. We have one instance of Fabric Connect per ISIS area, and we do support multi-area in this environment, so we can scale out to tens of thousands of nodes, and the geographic scale is limitless as well. We have many customers that have fabrics that span the globe. Fabric Connect data plane is Ethernet. Again, I want to repeat, there is no use of IP to establish topology or service delivery. So this compares rather starkly against the MPLS protocol architecture, but also note that we borrowed from the MPLS protocol architecture with this notion of directly labeling over the Ethernet structure. And by this evolution, we've been able to simplify the architecture drastically. And this leads to extremely fast automation and fast convergence times within the network architecture. And this translates to quicker service delivery and recovery. Let's take a look at how shortest path bridging, Extreme Fabric Connect, compares with the different IP fabric architectures. Again, a similar thing here. We reduce down to a singular control plane that's based on ISIS to control the SPBM topology. The same protocol is used at the service signaling level, ISIS, and Fabric Attach, which basically drastically condenses the complexity of the service signaling and control plane environment. Now we are down to a single protocol, basically ISIS, and a forwarding plane of Ethernet itself. Notice how we actually optimize in the overhead to support the same level of services, and we could argue greater density of services. And as we can see, the service plane and the ability to deliver these services can now be attained end-to-end across the fabric architecture with the total absence of any IP underlay, which the end result is a big boon to a security posture, because the core, the actual networking core, now becomes dark to intruder IP scanning techniques. And this is one of the major things that intruders like to do, is to enumerate your networking infrastructure before they begin their active attacks into the network and begin to compromise systems. They don't want to make noise. They want to be as quiet as possible in their procedures, in the way they ingress the network. And the only way they can do that is with knowledge. So this basically puts the intruders, quote unquote, in the dark. So let's take a look at the traditional model that we started with and compare it architecturally with what results at Fabric Connect. So in the old model, we see the top-down vertical dependencies and the house of cards and the complexities of provisioning, which can be easily seen. But then as we look at the Fabric Connect, everything collapses down into a very streamlined protocol model where we have ISIS as the single control plane, the data plane is Ethernet, Fabric attached for certain services, and then we can also see that all of the services, as we predicted and talked about in the beginning of the presentation, are atomized. And they're horizontally independent. So I can go in and I can create a layer 3 multicast service within an IPVPN environment, and I don't need to do anything with underlying service constructs in order to make that service delivery possible. And this in itself is what lends to increased automation. And while we're on that subject, I do want to have a note on automation. There are two types. First of all, we have explicit automation. And this is the concept of, you have a staff and they're basically building scripts to automate network service delivery. It does require manual effort, does require a testing too, if you're smart, because I do want to note that that's one of the reasons for a Facebook outage that happened recently, is they did not properly test the modifications of the scripts before they deployed. And it does require a relatively high amount of programming expertise, and as a result, it's a high operational expense model overall. Now, interesting to note that this is the method that's used to automate MPLS and also IP fabrics. Okay, so you need to basically do explicit automation, and this makes things a bit more complex in order to deliver things at scale across these different protocol architectures. Conversely, there's implicit automation. That's automation that's embedded into the network service delivery itself, and policy-based access provides the quote-unquote trigger for the service delivery work chain, and it provides or requires minimal programming expertise, and consequently this is a very low operational expense model. This is what Fabric Connect is based on. This is what shortest path bridging delivers, because in essence it is a programmatic Ethernet fabric. Consequently, we can do a very high degree of granular automation in that environment without the need for explicit automation practices. Now, I want to emphasize that we can run explicit automation on Fabric Connect, and I have many colleagues of mine, myself, we've developed scripts, things of that nature, customers do as well, but it's not required. A good degree of automation is provided implicitly by the fabric itself and the policy constructs, and I'll talk about that in some upcoming slides. So what are the benefits of the evolution? Because we've talked about several different protocol models, and we've kind of painted the picture that we've arrived at our goal. Well, what are those benefits? Well, first of all, we can provide an effortless networking environment, and this is very important for what Extreme terms as the infinite enterprise. And this is also important for digital transformation. So a zero-touch network deployment, consistent network access experience, provisioning at the network edge only with no need to address the requirements of the core. And as you can see on the right-hand side, we kind of show a purple circle around the environment. It's really Fabric Edge. That is the service access point layer. That's the only provisioning area, which means things can become very clean, gives simplified operations, single protocol for all the networking environments, and as a result, to the theory of a Fabric Edge service layer, we always have clean configs. There are no lingering configuration fragments, which can actually compromise a security policy or posture. Implicit end-to-end automation also removes the human error element, and this is important as well. We don't need to have provisioning manually. We also don't need to have Python scripts being written in order to deliver the service models that run across the fabric. And as a result, the overall maintenance for the day-to-day is drastically reduced. And this is important for customers like hospitals, municipalities, state and local governments, things of that nature, because they have a lot of other things they're doing than just running a network. Flexible topologies, and as we said earlier, this is one of the goals, a single protocol that can do campus core edge, the data center, the MAN, which is the metropolitan area, or the WAN, which is the wide area. And again, fast failure recovery because of the simplification of the overall protocol architecture. Because of this concept of the service provisioning layer, we're 11 times faster to provision services with simple edge provisioning. We no longer have to do the hop-by-hop provisioning, the high-touch core, if you will, and this also introduces a lot of potential for human error and outages as a result. Services in the traditional model are also directly coupled to the physical topology. You had IEEE routers where you made entries on interfaces and you applied subnets, and they were directly coupled to the physical topology. And as a result, SDN is largely used to hide the underlying complexity of the environment. But note that the complexity is still there, particularly when we're talking about the need to troubleshoot. With Extreme, it's edge provisioning only. The core is hands-off. Moves, adds, changes on the fly, no more maintenance windows, new services can be created, services can be deleted and removed. Services are abstracted from the topology, and that's the reason why the above bullet is true. Because services are abstracted from the topology, it's the ideal SDN architecture because it's only concerned with services. Topology is handled by Ethernet. Stealth topology, and this is the Ethernet-based forwarding concept. Unlike traditional networking, and this includes IP fabrics which have IP-based forwarding, Ethernet is only used within the fabric core. No IP required to forward traffic. The network topology is therefore dark when scanned. Breaches are contained and damage minimized by the MAC and MAC tunneling. So this becomes a very, very important trait. Keep the attacker in the dark, keep them nailed down with limited, well, actually no lateral movement outside of their local segment. Now, to automate, we basically use policies. So policy-based creation and access of the ISIDs, the individual service identifiers that we talked about earlier, which actually we term as virtual service networks or VSNs. You'll hear that term later on. Hyper-segmentation is used to isolate critical applications, and these are the VSNs, the ISIDs themselves. It denies attackers the borderless open environment to hop from one compromised system to the next. Extreme control policies provide dynamic mapping of users or devices to those segments, and this includes the VLAN and IP subnet identities as well. Dynamic mapping of network policy to users, thus very much less complicated in IoT, and OT environments become very, very streamlined in this model. And this provides an enhanced security without increasing complexity, which provides an overall increase in security posture without inordinately expanding the OpEx environment. Enhanced security with segmentation prevents lateral movements, creating dead ends for hackers. Without hyper-segmentation, isolation is fragmented, limited in scale. Largely, you're depending on VLAN, subnets, access control lists, and route policies. These can easily be thwarted. With hyper-segmentation, it's the MAC and MAC tunneling, the ISIDs, the virtual service networks that provide this across the entire network. And this is the case whether it is a local campus environment, a metropolitan area environment, or a true wide area global environment. We can do virtualization of logical networks over the fabric as well. And these are the virtual service networks, or the VSNs, that we talked about earlier. They can be of multiple personality types, and we'll talk about this for a bit. We have in the center a layer 2 VSN. We have a layer 3 VSN, which is combined with the layer 2 VSN on the left-hand side, representing a typical office environment, for instance. And then also note that we can provide layer 3 services for IPv6 as well without the need for any additional complexity to the protocol architecture. And again, this is because of the streamlined, atomized architecture of the fabric itself. So now we'll take a more detailed look at the summary of the Fabric Connect services. We obviously have the SPBM data plane environment, and then over that we have basically a GRT or Global Route Table IP shortcut environment. Largely, we recommend that those are used for the management of devices. The switches themselves, perhaps administrative interfaces for intrusion detection, firewalls, things of that nature. Great place to put the management domain, which is over and above and beyond the domains of interest of the devices and users within the environment. As a result, we provide a series of virtualized services. These are the virtual service networks that we talked about. And basically, we provide layer 2 VSNs and then also layer 3 VSNs. And the technical description of both is relatively easy. Basically, a layer 2 VSN is nothing more than a VLAN, which is associated with an ISID. That's it. And that ISID can be across the country, it can be within a campus, it can be any amount of scale of numbers of endpoints of the VLAN. And there are several different types that we're not going to go into detail on in this presentation because it would just take too much time. The secondary class, L3 VSN, is equally simple. And keep in mind that this is a true IPVPN environment. Normally, we'd need BGP, we'd have to peer, we'd probably need MPLS. Instead, what we've done is we've done all our peering using the ISID. That's it, which makes the layer 3 VSN dark. The reason why is the peering is Ethernet. It's an Ethernet circuit. Now, I want to emphasize that all of these services can be chained together as well. So here we see a layer 3 VSN, and then we also see L2 VSNs in tandem with it. All of these services can support multicast as well. And this is a very important thing to realize, is we do support multicast in all the models. And what we use in multicast is a distribution tree. And what is the distribution tree? Yes, you guessed it. It's an individual service identifier, an ISID. In conclusion, the evolution never ceases. And we're not done yet. Networking technologies have evolved significantly over time. It's important to open your eyes to that. A more streamlined and atomized protocol model has been the overall trend of evolution. Such a trend will lead to increased capabilities in automation and scale, which is increasingly important in digital transformation. Implicit automation within the protocol architecture itself will reduce the need for explicit automation and delivery of services. The removal of the dependency on IP underlay topologies reduces complexity and obviously improves the overall security posture of the network itself. Further evolution in Ethernet fabric technology will lead to more sophisticated services and the ease and scale with which they are deployed. Thank you very much for your time for this session. I hope you'll find that 10 years of fabric innovation have paid off, and the result of that evolution is available to you here and now. Thank you.